Okay, this title is internal force convection, but prior to this, okay, we need to assess, or you need to have access to the external force convection as well before internal force convection, because external force convection is also important, equally important phenomena in the industry and also in our daily life. Okay, so it is best for us to go for that one first before or prior to the internal force convection, which much more related to the flow in the pipe. Okay, let's see. Okay, for in external force convection, okay, we have this concept of drag, drag and lift. Okay, so this is the two important concept that makes the fluid, okay, flow in the what you call in the pipeline, okay, or in the pipe, or above or on the flat surface. Okay, so if you ever have what you call this aerodynamic setup, okay, whereby you have the air resistant, okay, and you will definitely, this one is aerodynamic, some sort of form lah, okay. For example, when you have a plane, okay, so basically there will be several forces, okay, that will be imposed to that particular aerodynamic structure. Okay, for example, you have this force that will tend to, okay, to bring back, okay, your body, okay, the body, okay, and the other one will try to push the body, okay, and you also have this force that tend to push it towards gravity, and also the force that will try to make this body floating, okay, or make the body um, in that particular direction. Okay, this is being called drag. Okay, this is thrust, and this is weight, okay, or gravity, and this is lift. Okay, so the one that normally will ensure the plane will be on the course is basically the forces of lift and thrust. Okay, so that your plane will move um, steadily. Okay, without any problem. Okay, so in the fluid we have to assess these two uh, well terms lah. Okay, we call it drag. Okay, the force that a flowing fluid exerts on a body in the flow direction. Okay, and the components of the pressure and wall shear forces in the normal direction to flow. Okay, so kalau flow tu direction dia macam ni, so normal to direction is inilah, okay, which is lift lah. Okay, that's why they call lift. Okay, so for the fluid flow we will have this drag coefficient in order for us to know the drag force of the fluid, or sometimes we might call this CF. Okay, this one is F, normally F lah. Okay, or FD for drag lah, coefficient drag coefficient. Okay, CD, and the FD is drag force. Okay, and V is velocity. Okay, the free stream velocity or upstream velocity, which refer to this one, V, this V. Okay, velocity is not, don't be confused with what you call volumetric flow rate. Okay, it is strictly velocity V. Okay, volumetric flow rate, normally the symbol is this one. Okay, do you have dot on the V? Okay, and you also have a density, okay, in the equation, and also the frontal area. Okay, so normally the frontal area, um, either from the cylinder or even for rectangular, normally it will be the same. Okay, if rectangular might be a l times width. Okay, so normally the frontal area is that lah. Okay, so drag coefficient can be associated uh, to skin friction drag or pressure form drag. Okay, either one lah. Okay, right. So this would be the flow over flat plates. Okay, the parallel flow over flat plates. Okay, that's why we call this external convection, because this convection happens openly, okay, at open space, okay, on the surface, at open space. So there will be uh, no boundary, okay, upper boundary lah. It's just the surface here lah. You have the surface here, okay, and there will no limit on top of this flow. Okay, so the interaction will be in terms of the flow and the surface. Okay, so there is no center whatnot lah in this setup. Okay, so this will be the Renault number. Okay, the Renault number is basically will be based on the point of interest. Okay, for example, if you have REX, we are referring this Renault number to a specific point within the 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 length of the plate. Okay, for example, if you ever want to have the Reynolds number at this point, okay, so that will be the value. Okay, this point X may be 3, for example. Okay, you want 3, and the row, what is the row, okay, at 3, and what is the V, and what is the mu, and you will get the Reynolds number for that value lah. Okay, and then normally for flat plate, okay, the critical Reynolds number is this value. Okay, normally. Okay, and this will depend on the surface roughness and the turbulence level and the variation of pressure along the surface. Okay, unless it's stated, okay, in the uh, in uh, in the paragraph or in the problem. Okay, you can always assume this as the value lah. Okay, all right. Okay, we are moving into much more specific in terms of the calculation. Okay, so we have local and average value of CF, or coefficient of uh, drag. Okay, drag coefficient. Okay, so whether it is local or average. Okay, and in local and average we got further you can be divided into further types, which is depends on the flow regime, which is laminar or turbulent. Okay, if laminar, this will be the formula, and this will be the formula for turbulent. This is the layer of boundary layer. Okay, how thick is that? Okay, and it will be based on the Reynolds number. Okay, don't forget that. And this one is for, of course lah, the value is for turbulent, and this one is for laminar. Okay, the conventional critical Reynolds number lah. That one is normally we will not apply this. Okay, unless if we ever want to know, or we are focusing on a specific point within that the a flat plate length. Okay, so what we much more interest is this average formula for average laminar or turbulent. Okay, you can use this for laminar flow and this for turbulent. Okay, will still based on the Reynolds number. Okay, for average. Okay, this means that if you ever have the plate, okay, you are referring to the Reynolds number of this plate length. Okay, from A to B, from point 0 to point L. Okay, that's now X maybe in between the point. Okay, this is X, X1, this one is X2, and so on and so forth. Okay, this one is for turbulent, this one is for transition. Okay, and this one is also can be used. Okay, but it will be referred to uh, the surface roughness. Okay, so this all this, okay, we can assume it as smooth surface. Smooth surface. If you ever have a rough surface, and you should consider using this equation, right? Okay, we proceed to the one that is related to the heat transfer. Okay, so basically, when we need to determine the heat transfer, what we can do is we have to determine the Nusselt number. Okay, because once you get the Nusselt number, of course you will eventually will get the value of H. Okay, again this one is local base heat transfer for Nusselt number, where let's just focus on the blue formula. Okay, I mean in terms of average formula. Okay, for laminar you have the same formula, general equation, okay, to state that when you got Nu, you will definitely get H, because H is something that we cannot determine by the properties of the fluid or the condition surrounding it. We will only know when we know the value of Nu. Okay, Nusselt. Okay, L and K is always been given to you, unless that question requires you to calculate that. Okay, so okay, again, it is being just now. If we have a drag coefficient, drag force, it is only related to Reynolds number. So this time around, it's also related to the Prandtl number. So you have to know Reynolds number and Prandtl number in order for you to determine the value of Nu. Okay, and might as well the same with the turbulent. Okay, and this one is can be applied for transition region. Okay, and for long plate. Okay, you can apply this equation, and this one can also be applied, but it's much more related to local because they have X here. Okay, and then this PEX. Okay, PEX is basically REXPR. Okay, REXPR, we call it PEX, okay, which being called Peclet number. Okay, this one can be applied to all fluids, but of course it is local equation or local uh, formula. Okay, for Nusselt number. Okay, so I think the most important part that I have to emphasize is this point lah. Okay, the fluid properties are evaluated at the film temperature. Okay, what does it mean by film temperature? Is basically the temperature in between the surrounding and the surface of the temperature. Okay, then from this TF, or sometimes we call it T reference. Okay, you can get the value of rho, K, Cp. You can also get Prandtl number from that as well. Okay, and all this is needed in order, and also mu. Okay, or sometimes they will give you new. Okay, so all this can be used to compute for RE normally. Okay, so by using this T reference, you will know the properties, the physical properties of the material at that particular temperature. Okay, and normally um, we will ensure that the pressure is fixed. Okay, I think pressure is uh, more or less ambient pressure. Okay, 180 m. Okay, so this one is very important. Okay, because we have to know the reference temperature. Where is the reference temperature? You can look at uh, the properties of the fluid. It's very important because it will determine this one. Okay, the region, whether it is laminar or turbulent. Okay, whether it is fully developed or developing region. Okay, all right. Then we have example number 1, which related to the convection. Not convection, is the drag coefficient or drag force. Okay, so basically, this would be okay. This would be the formula that can be used. Okay, for to solve this problem. Okay, so we know that the T infinity is 60 degrees C, and you have Ts of 20 degrees Celsius. Okay, and your velocity is V is equals to 2 meter per second. Okay, so you have to determine the drag force and the rate of heat transfer per unit width of the entire plate. So you know that your width is 1 meter. So you know that your A will be 5 meters square. Okay. So where do you need A? Why do you need A? Because the CD formula, okay, the coefficient of diffusion formula will have A in it. Okay. And you have to determine F, right? So once you know the value of C, okay, you will know the value of F, but you have to know the value of A. V is being given, rho is also being given. It's lucky for you. All the properties here is being given to you, so you don't have to find what is the reference temperature, whatnot. Okay, so what you can do is we just determine the Renault number. Number 1, you have to determine the Renault number. Okay, how to compute the Renault number? Okay, it's basically you just follow this equation. Okay, VLC over nu. Okay, so okay, VLC over nu. Okay, so V is 2, L is 5, and nu is 2.485 times 10 by the power of negative 4. So you will get the Renault number. Then you will look at the Renault number, whether it falls in between this region or this region. Okay, region or regime lah. Okay, if it happened to be this region, and then you can use this formula to get CF or CD, then you can always compute for FD is equals to CD, you times with this one. Okay, all is being given, rho is already been given here, V square, this is V, and then A is already being determined, and then you just multiply with the uh, value of CF, so you will get FD. Okay, and then you need to determine the Renault number, the Nusselt number based on RE. Renault value just now, it is laminar or turbulent, of course laminar, so we'll use this formula. Prandtl number has been given, Renault number has been you can always determine that Reynolds number, and then you can determine the value of nu. Okay, the value of nu. Okay, once you have the value of nu, you will know the value that particular of that particular h. Okay, so once you know the value of h, okay, you will know the value of q. Okay, by q is equals to h as, okay, delta t. Okay, delta t, which is ts minus t infinity. Okay, so 60 minus 20. Okay, so number 2 here, you have to determine cd or cf, okay, based on Reynolds number. Number 3, fd, okay, based on the formula. Number 4, nu, based on Reynolds number as well. And number 5, you determine the value of h from Nusselt number. And number 6, you can determine the value of q. So the ultimate objective of this question is to determine number 3 and number 6. Okay, so you have been given this answer. So please do check the solution and compare with your solution. Okay, please don't be afraid if the value is slightly different. I mean, in terms of maybe you will get this 11,070, for example. So don't be afraid with that value, because if you feel like your calculation is right, then it should be somehow a bit different because of the changes in the significant figure. Okay, some of you might using so many significant figures, some other will use the round up figures, so it will become much more different compared to one to another lah. Okay, so don't worry about that so much, right? What about cylinder and spheres? So we don't have that specific equation related to the CD, okay, or CF. Okay, what we have is the plot, okay, which you can associate this with the Reynolds number as well. So when you get Reynolds number, okay, you just choose whichever geometry that you are referring to. Okay, it's either smooth cylinder or sphere, or you can have any other type of for example of surface lah, because this one is basically will be based on the surface roughness, relative roughness. Okay, so this one is for smooth uh, surface. Okay, so for example, if you have like 10 by the power of 4 for the surface Reynolds number, okay, and then you will have this value. For example, if it is pure, if it's small cylinder, it's much more lah, the CD value. Okay, so we will look at the solution after this. They have an example, and then you also have this so-called smooth or rough, okay, based on Malik 2014. Okay, uh, basically this one is basically for cylinder, both smooth and rough cylinder. Okay, I think it's more or less the same with the one that we shown to you just now. Okay, Machingan and Gajah. Right, so they comes this one is mainly for drag coefficient. Okay, drag coefficient. So you have to determine CD. Okay, and then you will straight away will know the value of FD. Okay, they ask you to determine the drag force, right? So FD lah. Okay, so and all the condition, okay, all the properties has been given to you. and likewise the A is frontal area, which is L times D, okay, for the cylinder, okay, and the answer is 5.3 kilonewton, okay. Basically you need to determine the value of CD, okay, but the CD is already been given to you, so you will get this value straight away lah. Okay, it's very easy. You want to determine FD, right? So you already know what is the value of rho here. Then you have V is here, and you have A is LD, right? So L is basically 30 meter here, L. You times with diameter, so the diameter is 2.2 cm, so you have to turn up to be meter, convert it to meter, and you will get the value of A. So A, plug the value in this, okay, and CD is equals to 1, so FD is basically the same with this one, okay, so you will get the answer after that, okay. But if you ever want to test whether this value is right or wrong, okay, you can always check with Renault number, okay, and you will get around 7.7 times 10 by the power of 4, the Renault number, if I'm not mistaken. Please check, and you can refer to the chart I've shown you just now, this one. For example, if we ever go to much more, there is somewhere around here, right? So if we have 10 by the power of -4, so this one is 7 uh, at this one, okay? This one is 10 by the power of -4. 2, 4, 6, 8. So it should be in this area, okay? Okay, from this area, you just extend, okay, the line up until a smooth cylinder, and then it is in this area, in this region, and it become at this point. So it is being proved that the value of CD is equals to uh, 1, so at this point. And if you ever extend this, and it become just exact on the line, okay, so that is the answer. That is why it is 1, okay. So it's not really easily being assumed as 1, okay. So it's not as easy as that, okay. But just to uh, to save time, okay, we just end up with this value lah, okay. All right, now we have a cylinder and spheres in terms of heat transfer, okay. The Nusselt number just now is the uh, coefficient of drag coefficient, this one is Nusselt number, okay. For local, just now in the flat plate you have local, right? But this one you have local in terms of the chart, just like the chart being given to you in for drag coefficient, okay. They also have in terms of the Nusselt number for local. So we are not really interested in that, since we are not really using that Nusselt number in terms of local. So we are more interested to the average value, whereby we have this kind of equation, a very complex equation, but I would say it is much more so-called accurate, okay, if we were to compare with the estimated formula, because we have another type of formula I will show you after this. This one is for sphere, okay, and you have this other um, formula, okay, for Nusselt number as well, okay. For example, you have this general formula of C is the number in front, the coefficient number, okay, which turn out to be, if you look at the circle, for example, the cylinder in circle, for example, this value is C, okay, the front value, okay, so C is 0.027, 0.193, blah blah blah, okay, and REM is value of the power of Reynolds number, and the power of Prandtl number is always 1/3, okay, so no problem lah, and it's always this value, okay. So there we will have to no need to classify or categorize the flow regime, whether it is turbulent or laminar, and just go to the range, okay, whereby it is maybe 0.424 or as high as 40,000 to 400K for circle. And you also have square tilted, and any other form of uh, apa ni cylinder lah, okay, they call it cylinder, round cylinder shape, round shape cylinder, square, hexagonal, and so on and so forth, okay. So the respective value is that. So you have two formula here. This one is for cylinder, yeah? It's not for sphere, okay. So you have this formula and Churchill and Bernstein formula here, okay, right, to be more clearer, okay. And this one is much more tedious because it involves very much formula lah, okay, with that respective power and so on and so forth. This one is rather simple, but I can assure you that the estimation is not as good as the former, okay. So the second one is much more merely estimated, okay, but it can be used as well, but maybe it's not really accurate, and you have to be very careful with the range, okay. Sometimes it is above the range, the estimation is above the range, okay. Okay, let's see the example here, okay. If you ever look at this example, okay, let's see this example. A long 10 cm diameter, so the diameter is 10 times 10 by the power of -2, okay, 10 cm, oh sorry, 10 cm by the power of -2, okay. And then you have external surface temperature, the surface, okay, is at 110. You have T surrounding at 10 degrees C, lupa. And then you have no problem, pressure is ambient pressure, and the wind, okay, V is equals to 8 meter per second, okay, and L is basically 1 meter, okay, because they want the per unit of its length, okay, so that is why L is end up 1 meter, okay. So you have been given this properties, okay. What you can do, okay, is you have to pick what is the method that can be used to solve this problem, okay. As I've shown you in the previous session, okay, you have to extract all the information that like I did just now, okay, and then maybe you want to list up this one, okay. So first you have to determine the Reynolds number, okay. What is the Reynolds number, okay. Maybe we don't really care about the regime, because this kind of equation, they don't even bother about what type of regime, as long as you know the range of the Reynolds number lah, for this one no problem, okay. But it is for the purpose of to getting this equation done lah, because it is depends on the Reynolds number, so that is why we need that Reynolds number, okay. So RE Renault number is V D over nu, right? So V is 8, nu rho is 0.1, okay? Then nu is what? 1.896 times 10 to the power of negative 6. You will get around 42,000. Okay, so the equation that can be selected is this one. Okay, but I would also suggest you to do this as well. You will know why I asked you to do that. Okay, and this formula as well, the formula, the lengthy formula. Okay, so what you can do is get all this Nusselt number. Okay, like this one lah. For example, if you use this one, right? So you have Nusselt number 1, this one, Nusselt number 2. Of course, basically it is the same, lead to the same solution. Okay, Nusselt number 3 is this one. Once you get Nusselt number, you will get H1, H2, H3. H1 method 1, H method 2, H method 3, and you will get Q method 1, Q method 2, and Q method 3. Okay, so you try to compare all the answer. So you will get later on, you will, of course, this answer will be the best one because it is the estimation is there, the detail is there. Okay, for the estimation like this one, okay, it happened to be this one is much more closer than this to this rather than the other one. So that is why I mentioned to you just now. Sometimes the Renault number is 42,000, so it's quite close region. Okay, I mean in between the range might have some sort of what you call discrepancy. So sometimes you can always estimate based on the range, but the ultimate solution does not mean that it will fall under that range. Okay, but if you didn't know that, because this one you have to go one by one, so it's quite a tedious activity or tedious way. Okay, you can always rely on this as estimation only. Okay, no problem. Okay, and you, if you want to save side, and then you have to use this one, the lengthy one. Okay, right. So the answer, based on the calculation, I think I use this one. So it will be 1093. Okay, please, please do I what I have proposed to you. Okay, you, and then you can see the difference in terms of the estimation. Okay, and that's the beauty of the formula lah. And don't try to remember this because in the final assessment, inshallah, it will be given.